Okay, so in the previous analysis video, we saw that sequential formulation of limits of functions, and also we saw algebra of limits where we add, subtract, multiply, divide one function by another function, and then we figure out limits of those combinations, algebraic combinations. Now let us start today's discussion with two special and very easy limits. One of them, of course, is this. The limit of a function which is constantly c. So that means the function is defined to equal some real number c at all the inputs, all the real numbers. The limit of this function at any real number x naught in the set of real numbers is equal to c. This is one limit, and another limit is this. Here the function is the identity function. Now to establish these two limits, we need not use the definition of limits because we have our sequential formulation of limits, that is this proposition 939. By this proposition, to show these two limits, it's enough to consider any sequence in R that converges to x naught, say an is a sequence of real numbers, and say this converges to x naught. Then if we can show that the functional values of these sequential terms under this function, that will those values will also give us a sequence. If that sequence converges to c, then by this proposition the limit will be c. The limit will exist and it will be c. Now what shall we get if we apply the function? Although we haven't given the function any name, it's the constant function, but you can understand that if you apply the function to these an's, then you will get this constant sequence, and that constant sequence, of course, it converges to c, and that's what we want. So by this proposition, this limit is it's true. Similarly, say again this is any sequence converging to x naught. Now if in place of that constant function we apply the identity function on the terms of this sequence, what do we get? Which sequence are we going to get? We are going to get back that same sequence an, and that of course converges to x naught because originally that's how it was chosen, right? So that's why again by proposition 939 we have this limit. So now using these two limits and using the algebra of limits, which is the last proposition that we saw in the previous video, this is proposition 9314. We can calculate limits like this. For example, limits of polynomial functions, say this quadratic polynomial, using all the parts of this proposition, that is the part which involves sum of two functions, then product of two functions, multiple of a function by a real number. So using all those parts, you can clearly see that this limit will be this. You can do it in steps. Say first you apply the first, I think it was the first part of this proposition, which says that the limit of the sum of two functions is equal to the sum of their limits. You can use that 2 times here, and then you can write this limit as limit of x square plus limit of cx plus limit of d, and then you can then subsequently use the other parts, and then ultimately you will get this. Now after this there is a little kind of remark. Let's see what that remark is. The remark is this. It's not an actual remark, I say kind of remark because it's just written as a sentence. It's not coming as a remark with, it's not an item. So again, like before, E be a subset of X and X be a subset of R, our usual setup for limits. Let X naught be an adherent point of E, and let L be a real number. And suppose we have this limit. Equal to L, but of course I forgot to say anything about f. F is a function which is real valued and has x as its domain. So that means f converges to L at x naught in E. Okay, now suppose you have another set Y which is a subset of E, and it turns out that x naught, just like it's an adherent point of E, is also an adherent point of Y. If you want to see how this is possible in a specific case, you can consider this. Say you take E as this closed interval. Okay, we know that 0 is an adherent point of E, but instead of considering the entire E, you can consider this subset also. We take 1/2 of the interval, and you can clearly see that 0 is an adherent point of this new set, this subset as well. Now the claim is that the author is claiming that in that case we will also have this limit. That is, we are just replacing E by Y. But how? That we will see now. It's not anything difficult. You just have to write down the meaning of this limit, and from that it will follow easily. But it is something that can be useful. The only thing that you have to keep in mind is that the original set E had X as an adherent point. The subset Y should also have X as an adherent point. Okay, that should be kept in mind. So we are now given this, which means what? For every epsilon greater than 0, there exists another positive real number delta such that the distance between f of x and L is at most epsilon when x is coming from this intersection. And this implies that the distance between f of x and L will be less than or equal to epsilon when x belongs to this intersection. So we are replacing E simply with Y. What is that value? Can it be done? Of course it can be done. Why? Because Y is a subset of X. So for all X coming from this set, this inequality is true. So in particular, if those X are coming from this intersection, which is a subset of this, since Y is a subset of E, also this inequality will be true. Okay, so this is a special case, and that implies this limit. So this is just one small thing. And now let us look at some examples, actual examples. And the example that comes after this is, I can write here itself. Line 3, 16, item number 16. We just need to write the function. The function here is that you may already have seen this elsewhere, the signum function. I think it's called the signum function or I don't think it's called signum function. Anyway, what it's called is not that important. What the function is or what it does to the inputs, that is important. That is the rule for the function, which is this. It is defined to be equal to 1 if your input is positive. It's defined to be equal to 0 if your input is 0, and it's defined to be -1 if the input is negative. Obviously this is a well-defined function. Now the question is this: what is now there are 3 limits that we will consider, 3 limits depending on that E, that set E that we are going to change. One of those limits is this. X approaching 0, X belonging to the set of positive real numbers. This. Let us first figure out how we are getting this. Now, instead of using epsilon delta actual definition of limits, we can again use proposition 939, that is the sequential formulation. For that, what we need to do, we need to take any sequence, remember any sequence, okay, any sequence in this set that is converging to x naught. So because I say any sequence, you cannot take a specific sequence, it has to be general, arbitrary. So let an be any sequence in this, which means all the terms an are positive real numbers converging to 0. An example of such a sequence is our familiar 1 over n. There all the terms are positive real numbers, in fact rational numbers actually, and that converges to 0. But there may be, actually there will be many such sequences. Okay, now what about this sequence? Because all the ANs are positive, so this sequence will be the constant sequence, all of whose terms are equal to 1, and that of course converges to 1. So by proposition 939, the limit is 1. So that means this is justified, and you can easily understand that by a similar argument, we also have this other limit. Instead of focusing on the positive part of the axis, we can also focus on the negative part, and on that part this limit will be -1. Again, similarly, if you take in place of an, you say you take a sequence bn, any sequence bn whose terms come from here, and then you calculate the SGN values of the sequential terms. All of them will be -1 because they are all negative real numbers, and that constant sequence -1, -1, -1, that converges to -1. So again by proposition 939, this limit is -1. And now we are going to consider another one, where instead of having these half lines, that is rays, we are going to take the entire real line. That limit, however, would not exist. We will now see why. So what the author is claiming is this. I have written 0, no? Okay. Now I have the habit of wrongly writing in place of 0, x0. Sometimes I do that. This limit, tau says, does not exist. Suppose it exists and is a real number L. Then if it exists, because you see, proposition 939 works both ways, right? You can use it to prove that some limit is something, or you can also, if a limit is given, you can use it to say something about sequences. And in fact, I think after stating that theorem, although we are yet to see the proof, we will do it in the exercises, we mentioned this in a remark. Okay, so that thing we are now going to do. So because we now have the limit available to us, let us consider these two special sequences. Here the sequences start from 0, the index starts from 0, but here it starts from 1, but you already know that that is not a problem at all. You can make a slight change here. You can write in place of n, you can write n plus 1, then you can start n from 0. It's not going to affect anything. Now these two sequences are sequences in R, of course, they are real sequences, and both of them converge to 0. However, but then by proposition 939, the functional values of the sequential terms are going to give you two sequences that have to converge to L by proposition 939. So what are those sequences? One of them is this, which is going to be what? Because all these are positive real numbers, so it is the constant sequence 1. And we know that it converges to 1. And what is the other sequence? The other sequence will be the constant sequence -1. But now proposition 939 forces us to conclude that L is simultaneously 1 as well as -1. That is, we must have this. And this is absurd. It's an absurdity, a contradiction. So that means our supposition is wrong. So this limit actually does not exist. Here is another example. Here again another such function partly defined like the SGN. The function here is from R into R, and the definition is this. The rule for the function is this. It is defined to be equal to 1 if x is equal to 0 and is 0 if x is not equal to 0. So if you imagine the graph of this function, the graph is almost the entire x-axis, which is why the graph is almost invisible, but with one difference. At x equal to 0, the function suddenly takes the value 1. So that means it's the entire x-axis from which the origin has the middle. If you say so, the middle point, the 0 point has been removed, and in its place you have an isolated separate point at the location 0, 1. Okay, now for this function, let us, here also we are going to consider not one limit but actually two limits. There we considered 3, but here 2. One of them is this. Again at 0, but our first set E is going to be the set of all non-zero real numbers. And we claim that this is equal to 0. Again we take the help of proposition 939. So you take a sequence, any sequence here. That means these ANs are all non-zero real numbers. That converges to 0. Because all the ANs are non-zero, by the definition of F, what will be this sequence? It will be the constant sequence 0. And that of course converges to 0. So by proposition 939, this limit actually is 0. Fine. But now comes the other thing, the other limit, which you can probably guess which one we are going to take. Instead of this, we are going to take R. this is undefined or does not exist. That is the claim, but say it exists. Well, in this case we can prove it directly like this. You see, what does proposition 939 say? It says that if you take a sequence an like this in R, that means just a sequence of real numbers converging to 0, such that f of an also converges to some fixed value, then the limit exists and is equal to that fixed value. However, if that does not happen, because we have implication both ways, if that does not happen for some specific sequence, then you can conclude that the limit does not exist. Now let us look at this sequence. 1, 0, 1 over 2, 0, 1 over 3, 0, 1 over 4, 0, and so on. You understand the pattern. If one wants, one can write it in a compact form also by defining an properly. Okay. So it's, I won't say it's an alternating sequence, it is not, but it has two types of terms. If your index is starting from 0, if the indexing of the sequence starts from 0 or from 1, it actually does not matter. Say it starts from 0, then here you have 0th term, first term, second term, like that, right? In other words, if you are calling these terms Bn, say, where n starts from 0, then the even indexed terms, that is B2n, those terms go like this, 1 over n. They are reciprocals of positive natural numbers. But the odd indexed terms are all 0. Or if that sounds somewhat strange, you can just simply call this B1, B2, B3, etc. Then the odd indexed terms are the reciprocals of positive natural numbers, and the even indexed terms are just 0. It's not very difficult to prove that this sequence converges to 0. Fine. But now what are the f values? You next think of this. This sequence, it's a very sloppy way of writing, but you understand what I'm trying to do. This sequence is equal to, you see, at the non-zero values, the f values are all 0. So this will be 0. But when your input is 0, the f value is 1. 1. This is non-zero, so again 0, 1, 0, 1, and so on. This is an alternating sequence, and we already know that this sequence actually is divergent. It does not converge to anything because it's not a Cauchy sequence, so such reasons are there. So by proposition 939, this limit does not exist. Okay, so that way also we can conclude this. Now, again we are going back to the main idea of limits. When you see this, you obviously have the natural idea that the limit of f being L ultimately depends on the points near x0 but not very far from x0. In other words, the limit is a local concept. what is happening near x naught is what matters for this limit to exist and to become L, and actually that is the case. So this next result is about that limits are local, and it's a proposition. Nine 318, and it's been given a name also accordingly. Limits are local. Let me use some more ink. I think I am running out. This is actually a very useful result and will help us avoid many complications that you may encounter while calculating limits of concrete functions by removing unnecessary complexities from near x naught by focusing very close to x naught, thus removing those things, those problematic points that may lie somewhat near x naught but not near enough. So according to our current practice, here also I won't give the formal statement. Instead, I will just show what it says. So the beginning is again we are going to need all these things, E, X, and all those things. So we have these sets. X naught as before is an adherent point of E. F is a real valued function with x as its domain. What else do we need? We need the limit L, which is a real number, and we will now need another new thing, a positive real number delta. Then the proposition states this: the limit of f of x at x naught in E is equal to L if and only if this limit is also L. So what does it say? It says that you have your ordinary limit and the limit is L if and only if this other limit is L as well. What is the difference? The difference is in this part. Instead of allowing x to come simply from E, you are making it more narrow by focusing very close to x naught, and that closeness is given by this delta. You choose a very small delta so that you are again taking x from E, that is there, okay, but at the same time you are also focusing in this region only. Then that doesn't change anything. That limit will still be L, and if this is L, then this is also L. And this implication, that is going from this limit to this limit, is what will be useful for us. That's because you see, you can imagine roughly I am going to say Suppose this is your real line and you have E somewhere, okay, you have E, say, and say this is your x naught. So you want to know what happens to the functional values as your x is close to x naught in a specific sense which we already know. But say there are some points which are somewhat problematic that are also near x naught, and also those points are inside E. Now you can avoid those points. Say those points do not get very near x naught, that is, there is still a hope that around x naught in a far smaller region those problematic points are not there. So you can then choose that region as this interval by choosing delta small enough so that those problematic points can now be avoided. And then you consider the intersection of this and E. E, of course, here I have just simply considered this portion, but E may be more complicated also. But then you now you no longer have those problematic points. So by your usual calculation, you prove that this limit exists and it is L. Then this proposition guarantees you to conclude that this limit also exists and is L, in spite of having those problematic points near x naught and in E. So that way we can use this proposition. And its proof is an exercise that we will see in the exercises. Now after this, there is one example. This next example uses algebraic combinations of functions. That is, you are given two functions. This is going to be item number 19. You have two real valued functions of a real variable f and g. And the rules for the functions are these. F of x is x plus 2 and g of x is x plus 1. Then very easily we conclude these two limits almost immediately. This is going to be 4 because it will be 2 plus 2. You already know the rules. Similarly, the other limit for g is going to be 3. And so, by the algebra of limits, if you look at this function, you see, what we now want to do is we want to look at the quotient. This, however, we cannot do on the entirety of R. Why? That's because x plus 1 vanishes at x equal to minus 1. So that's why instead of considering the entirety of R, we can remove minus 1 from R and choose a smaller e and have this limit. X is still approaching 2, but now x is being taken from R, from which minus 1 has been removed. There is a small mistake in the text where the author has removed 1 from R. that will be minus 1. So now by that quotient rule from algebra of limits, this will be what? 4 over 3. Oh, and I also forgot to say one thing about a previous example. I will say it now. Right now I remember. It is that, let us recall that function again. Whose value is 1 at 0 and 0 elsewhere. Okay. So what did we conclude about this function? Let me write that. We concluded this, right? This, but this does not exist. Now a function for which this limit exists is said to have a removable discontinuity or a removable singularity at that point. What these words mean, we will see afterwards, but you can, well, you already know what these words mean, but let me just show you in picture what we mean by this. In the next section, we are going to discuss the idea of continuity, but even now itself, you can of course roughly see what that means. So what is the graph of this function? Say this is our 0. Just in order to show the graph clearly, let me just not draw the y-axis. So this is your usual x-axis. So the graph of this function is the entire x-axis from which the point x equal to 0 has been removed. And in its place, you have a single point which is at a distance 1 from the x-axis and above the x-axis. So this is the graph of our function. What do we mean when we say something is continuous? It means that it is not hindered by anything, it's unbroken. This, however, is broken, but it can be fixed by redefining this function differently at this single point. So instead of defining it to be equal to 1 at x equal to 0, one can redefine. The redefine means it will change, the function will change. One redefines it to be 0 at 0 as well. Then this brokenness goes away, or you can say it's removed. Okay, so the discontinuity that is created by this extra point, extra output 1 can be removed. So it's a removable discontinuity, or such points are also sometimes called singularity, although this term is used more in complex analysis, but we have singularity in real analysis as well. Removable singularity. So it is just something that the author mentions. And then there are two more examples. So let's go through them and then this section will be over. The next one is 20. The function that we have here is this. The function is well defined because that one point which could create a problem is not there in the domain. So you can see that because of that, for every value of x in this domain, x minus 1 is a non-zero real number. And you know from elementary algebra that the numerator of this expression factorizes like this. And so after cancellation you have this. So really the function is just this, and which is why one can now find its limit at 1. And you can clearly see that this limit will be equal to what? 2. This particular example may be slightly confusing at once when you see it for the first time, but no need to get confused. You always, whenever you have a confusion and it feels like there is something wrong, you go back to the definition. What is the E here? In the definition we have those ingredients, right? We have the set E, we have the set X, we have X naught where we are calculating the limit, and we have the function and we have the limit, that real number. So here E is this set, and what is X? X should be the domain of the function. X is also that set, so that means in this special case E is equal to X. Okay, what is 1? 1 should be an adherent point of E. Is it true? Look very carefully. Okay, we have to really, we should not take anything for granted. Our set is actually this interval, right? Union this other interval. When does a real number become an adherent point of a set? There is a definition for that, but more effectively, if you find a sequence of points in the set which converges to that real number. And one such sequence, of course, it lies on this part, is 1 plus 1 over n. This is a sequence in your set that converges to 1. So yes, 1 is an adherent point. See, the slight confusion that arises here is one may think that 1 is not there in the scene. So how can we take limit at 1? Do not forget that 1 only needs to be an adherent point of E. The condition that you have in the actual definition of limit, somehow, because of some reason, at least to me, creates the illusion or the wrong impression that x naught, although it has to be an adherent point of E, somehow we feel that x naught must lie inside x. No, that is not necessary. Psychologically, the fact that this is small x may make you think like that. Okay, x is coming from x. But here you can clearly see that x naught actually need not be a point of the domain at all. Still, limit is well defined and it exists also. So this example is important. And now there is this final one. Let me write on that side. This is also a partly defined function, a pathological one and a very bad one. And this last example is actually the function is well known and is used every now and then to create counter examples to situations. So the function is this, again from R into R, but now the rule for the function is this, if your input is rational, then the function takes the value 1. But if your input is an irrational number, then the function takes the value 0. And the author claims that this limit does not exist. To prove this, of course, we are going to take the help of proposition 939 again. That is the sequential formulation of limits. And we are going to look at two special sequences. One of them is this, our very familiar friend 1 over n. It is a sequence of real numbers that converges to 0. But what about this sequence? Note carefully that these are not just real numbers but actually rational numbers. So by the definition of our function, this is the constant sequence 1. And so, this starts from 1. So this converges to 1. But this is just one sequence. There may be other sequences that also converge to 0. And one such other sequence is this. Never fall in the trap of concluding just from this that the limit exists by proposition 939 and is 1. No, that will happen only when in place of this specific sequence you take any sequence. Okay. But instead of this 1 over n sequence, we could also consider this cannot take n equal to 0. We can consider this sequence as well. This also converges to 0 and is also a sequence of real numbers. But now the terms of this sequence are all irrational numbers due to the presence of root 2. So this functional values will give you the constant sequence 0, and that definitely converges to 0. So two different sequences give us two different points to which the functional value sequences are converging. So that's why by proposition 939 the original limit does not exist. And that's how this section ends. After this, we have the exercises where we are going to prove the results that we discussed in this section, and there are some other things also in the exercises, which we will see in the next analysis update, that is this coming Sunday. And our next upload is this Tuesday, and Tuesday let's go back to field theory. So that's just it for tonight. So I sign off. So see you on Tuesday with field theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.